Okay. Nice to be back. We will get started. We're going to pick up, the TAs told me we didn't quite finish the last video. I'm told you guys did the Ironman problem, the heat loss. You figured out that people should get hypothermia if you didn't account for like their body generating energy, right? But your body does generate energy, so you don't die. Now let's do our next clicker question. Well, I guess we'll start with, so this is the clicker question for the day, and it is as follows. So this is Fick's second law, and we're going to do it with thermal transport, right? So I'll kind of walk through this with you guys. It says, if a diamond at room temperature is placed on a hot plate, where its surface is heated to 100 degrees Celsius at time t equals 0, how long would it take for the diamond to reach 80 degrees Celsius, 1 millimeter within the surface, within from the surface, I guess I should say, in the thermal diffusivity of diamond is given as 11 centimeters squared per second. Give your answer in milliseconds. So just to help you get started, jog your memory on this. Because we asked the question, let's see, where is it? How long would it take, right? We say that it's initially at some temperature and that it's changing. You know that this is Fick's second law. This isn't Fick's first law where the temperature change isn't changing. The temperature is definitely changing here, so you have to use Fick's second law. And the only scenario that we gave you in this class is one generic solution. There's infinite solutions to this thing because there's lots of different boundary conditions. The solution that we gave you looks like this. It says the temperature at some position x, we can solve for it with this equation. We need to know the temperature deep within the material, T naught, and then you've got temperature at the surface minus the temperature deep within the material, T naught. That's going to equal 1 minus the error function of x, the distance at which you're making the measurement for Tx. And this is going to be divided by 2 square root of not d, but alpha t. So that alpha is the biggest difference I need you to remember. When you're talking about Fick's second law, if you're doing mass diffusion, then you use d, right? But for thermal transport, you use alpha. Right? That's the only difference between these. And I think that's pretty remarkable that mass and heat can both be modeled the exact same way. They both diffuse through materials with the exact same equations, right? There's different coefficients, right? The rates are different, but it's the same mathematics, which is pretty awesome. Okay, so to do this question, we give you the thermal diffusivity of diamond. We tell you the temperatures. We give you x. You know everything except for time, so you can go ahead and solve for time. The one thing that you will need is this table. Oh, dear. There it is. You will need this table to do the error function. So go ahead and get started on this one, and then we'll work it out together. Again, you're just giving your answer in milliseconds, so same thing that says here.
You say room temperature is 20 or 25 Celsius?
Good question. I think I usually use 25 Celsius or 298 K.
Book says 20.
Do they? We're closer to 20 here in Utah, honestly, except for in the summer. No, 25 for this one. And I always give a range on numerical answers, so it shouldn't matter which one you use.
I know you're going to sleep for this. There's a costume.
On this. I saw that as I was reading it.
Yeah, I'm that guy. I'm sorry.
It's got to be fixed.
I never want to be that
It's Anybody need help? We've got TAs. Okay, yeah, so it's y minus y1. Let's say where 1 and 2 yeah. On the right hand side of the equation, you've got 1 minus. So I've got air function over 1 minus If this is difficult to read, make that a little bigger. Everything inside the error function, if you plug in millimeters at the top and centimeters, squares, then you got millimeters and centimeters. That's how many meters. So you can convert them either way. You put them both to meters, put them both to millimeters, put them both to whatever you want, but you have to convert something.
So from centimeters to millimeters is what? Just one meter?
Yeah. 1 millimeter, 1 centimeter. Yeah. What's up, Frank? Okay, most people I think are getting this, but let me just announce it again. Inside the error function, this needs to be unitless, right? Just like natural logs and logs, you can't have units left over. They need to cancel out, technically. Here, make sure that this is unitless. And x is given in millimeters in the question, but alpha is given in centimeters squared, right? You're going to take the square root of something that's centimeters squared per second times second. So the units coming out of this denominator are going to be centimeters. So if you've got millimeters up top and centimeters on the bottom, you're going to have a problem. You won't get the correct answer. So make sure that you go to one or the other, right? You put them both to millimeters, put them both to centimeters. Take it to whatever unit you want, but they have to be the same or you'll get the wrong answer. Okay, so we'll do another maybe 2 minutes. We'll wrap this one up and then we'll do another example. Okay, we're going to wrap this one up. Get your answers in. We'll close the poll. I think people are basically there. Okay, what do we get? So answers range 3.92, 91, 9, 95. These are all correct, right? So over half the class is getting it right, and then there's some that are off. So what's going on here? We know that the error function is equal to, the error function of z is equal to this value, 0.2667. So it's between these two values over here. What we need to find is what z is, right? We know it's going to be between 0.2 and 0.25, and it's going to be closer to 0.25. The way that we can solve this, again, is with our linear interpolation formula, right? The linear interpolation formula says that y minus y1 over x minus x1 is equal to y2 minus y1 over x2 minus x1. What are these values? The value below and above, this would be x1, that would be x2. Over here you've got y1 and you've got y2. So doing that, what do you come up with for our value of x? What does x come out to as? 2439?
I got 239.
239, anybody else getting that? 240, all right, it's basically that. So that's what equals x, or what we're calling in the table, we're calling that z. Now z is also equal to everything inside the error function, right? So that's your x over 2 square root of alpha t. So again, we're going to make sure that things cancel out. So I'm going to convert x to centimeters, right? So we're going to say if it's 1 millimeter, that's 0.1 centimeter over 2 times 11 centimeters squared per second, multiplied by how many? Oh, we're solving for t. Okay? And when you solve for this, I think I end up with my t being 3.92 milliseconds, or 0.00392 seconds. Okay? Anybody not getting that? Anybody confused on that one? Or anybody not see where they went off? Okay, let's do one more question. This one's a little bit tricky, so we're going to maybe just set it up. Here's what it says. It says you're designing a component made of an alloy that has nickel and copper in it. Unfortunately, when you first synthesize this component, maybe you cast it or something and you melt it and pour it into some sort of mold, you notice that it's not completely homogeneous. In fact, you see that the composition seems to vary significantly over a distance of 0.005 centimeters. If we looked up the phase diagram of copper and nickel, which we've seen over and over in this class, right? As you go from pure copper to pure nickel, when you cast it, if it's some mixture between, as soon as you go below that line, this solidus line, it should be a single composition, right? Because this is a complete what we call solid solubility all the way across. So the fact that it's not that means that there's something wrong, right? It should be that. So because of that, it says one of your engineers suggests you could probably just heat treat this alloy, maybe at 8 hours, 1200 C, to homogenize it. Basically, you're going to say that there's regions that are rich in nickel, they're going to diffuse to the regions where it's rich in copper and vice versa, okay? However, this is a costly heat treatment, right? You'll learn in industry that anytime you have to heat something up, that any step you add is costly. And if it's a high temperature step, then it can be very costly because furnaces have furnace elements that burn out. It's a batch process, you can only fit so much in there. So you'd love to not do that. And if you have to use it, then you'd like to do it for a short period of time at low temperatures, right? So one of the problems they're seeing is they say when you do this, you notice that it sometimes causes it to locally melt, right? It's locally melting, that's one problem, right? And the other is the cost. So your task as an engineer is design a new heat treatment for this component that will prevent melting while minimizing furnace cost. And this is the information you're given. You can assume that as you reduce the temperature below 1200 C, the cost per hour for running this furnace is cut in half for every 100 degrees that you go down, right? Somewhat of a complex problem, right? So I want you to turn to your neighbor and just talk big picture stuff. How would you begin setting up a way to get a solution to this problem? Okay, let's go ahead and give this a shot. Anybody feeling brave and want to volunteer? What might you do, even if it's not right? What do you think, Josh? You have to heat it up to do what to that? Oh, that's a good guess. So yeah, basically you're saying, okay, you quenched it. What if you just heat it up back to when it's a liquid again? Yeah, that's a good guess. We can actually get away with doing less than that though, because we know that diffusion can also happen, right? Things can mix in the liquid state, but they can also mix in the solid state. And melting it, we decided that ruins our part. Local melting ruins the component. So let's not do that. Let's avoid that. That's a good guess though. We'll chuck you a candy all the same. Or the guy behind you. Right? Anybody else got a thought? What do you think, Brennan?
You want to look at your steady state, the D naught equation, to figure out just how dependent on temperature each one of these is.
Yeah, that equation looks like this. It says that our diffusion coefficient, which is going to be important, that equals D naught exponential of our activation energy for diffusion, we'll call that Q sub D, over our gas constant R times temperature in Kelvin, right? From that basically tells us if we know those values for D naught and Q sub D, we know that we can figure out diffusion at any temperature, right? So, yep, we need that. Not even, kind of close. All right, what else? What are you going to do, Rob?
Once you have that, you have to do a cost equation, figure out how much.
We need a cost equation, right? We need to write some sort of equation that gives us a cost per hour as a function of time. How do we do that? Anybody have a thought on that one? That's the hardest part of this problem, I think. I wouldn't put this on a midterm because I think that's a little bit too hard for this class. But how would you do that? Anybody have a thought? What's that? Piecewise?
Yeah, you know, a step function.
I don't know what that is. Brennan, you got an idea? Or somebody else hadn't said something. What do you think, Arthur?
Well, you look at the fuel to produce the heat, right? And then you check how much dollars is per kilogram or per something.
Yeah, let's write this. Let's say cost per hour, CPH. We'd like to know what that is as a function of temperature, right? So we know that it's equal to the cost per hour at 1200. But what do we have to then do to that? We have to half it for every 100 degrees below 1200. Mathematically, anybody want to give that a shot? Anybody know how to do that? It's tricky. I had to look it up. Takara?
You have to do something with like a floor function
The floor function?
or like a ceiling function.
Oh, like in Excel or something.
Well, I mean, like if it's like 12, if it's like 1100 degrees, you drop it down to 1000.
Oh, that would be one way. There's a better way. What do you think?
Would you multiply it by 1/2 to something or something?
Yeah, that's it. That's it. You're gonna say this is just like compound interest. If you think way back to whenever you last saw compound interest, you've got the initial amount, like the deposit that you put in the bank. That's this value. That's our cost per hour at 1200. Then you're gonna do 1, and then it's usually plus like the rate of increase. This time we're decreasing as you go down in temperature. So it's gonna be 1 minus 1/2, and then we're gonna raise this to. It's going to be our temperature 1200 minus our temperature, right? This is going to be raised to the 1200 minus temperature, and then we're going to divide that by, divide that by 100. So for every 100 degrees, that we are less than 1,200, it's going to cut our price in half, right? If you don't believe that that works, we can plug it in and see, right? If you assume that 1,200, if that costs, I don't know, $10 an hour, just making up a number, if that costs $10 an hour, by the time that we go down to 900, what should it be? We should half it once, twice, 3 times, right? So we're going to do 10 divided by 2, divided by 2, divided by 2. That should be $1.25, right? That should be $1.25 per hour. And again, if you plug that in here, if you plug in 900, it will be $1.25. So take my word for it on that one, if you haven't seen these compound growth equations in a while. Now what do we do? Anybody got another thought? I think somebody gave an answer. Oh, Arthur did. What do we do next? Brennan, what do we do?
So now that you know the dependence on temperature of both D and cost, you want to relate the two by figuring out just how much your flux changes for any given temperature.
Yeah, you're on the right track. Where are we going to use this? When it says the composition varies over 0.05 centimeters, that's a pretty specific value. We're probably going to use that in the question. That is, so remember, if you remember going back to our diffusion notes, we gave you a great big caution sign. We said a general or an average or a ballpark number for diffusion length, we call that x. And x is approximately equal to square root of d multiplied by t. So if you know that you need atoms to diffuse on the order of a distance x, then you can solve for x by plugging in square root of d times t. Okay? So in this problem, we know that we're going to have to, if you run it at high temperatures, you don't have to run it as long because diffusion's faster, right? So that means less money, but higher temperature means more money, right? So there's this balance. And then at low temperatures, diffusion is slower, but you're probably going to have to run it a lot longer, right? If diffusion goes down, to get to the same x, you're going to have to go longer. So what you need to do is you can solve this lots of different ways. I just did it graphically, right? I punched in a bunch of different temperatures and looked what the trend line was doing. You could also solve it analytically. So why don't you give this a shot? And then the last thing you need to know is, how do we make sure it doesn't melt? How can the phase diagram tell us what temperature we shouldn't go above? If we knew the exact composition everywhere, then we'd just know that we don't cross this solidus line, right? We don't know that. So what we're going to do instead is we're just going to take the melting points of the end members, right? If some region happens to be pure copper, for whatever reason, and you know the melting point over here of pure copper, and you know that it's 1082 Celsius, then pick a temperature for your annealing step, which is never over 1082, right? Make sense? So your temperature, set an arbitrary cutoff, say I will never go above temperature 1082. I will look at temperatures below, and then do a cost analysis, right? Using the information given here. So give that a shot, and let's see what people get. Oh, sorry. You need to know more information. You need to know D naught and QD, right? So D naught and QD, you need those. So you can look up these values. Nickel diffusing in copper, or copper diffusing in nickel, those values I'll write here. For the activation energy for copper in nickel, that is equal to 4,488 joules per mole. That's the activation energy. The Q for nickel in copper, that's equal to 242,416 joules per mole. And then the D naught for both of these, that's equal to 0.65 centimeters squared per second and 2.3 centimeters squared per second. So first let me ask you this, which one's going to diffuse faster? At any temperature, which one should be going faster? Copper should go faster or slower? Well, this is interesting actually. So in one case you have a lower activation energy. This one has the lower activation energy. 242 is less than 257, right? And it has a higher D naught in front of it. So nickel and copper will always go faster than copper and nickel, right? So if you can fix the composition gradient by either copper moving or nickel moving, let's go with nickel, right? Let's focus on this one. Let's ignore the other one. This one's going to be much faster because it has a higher pre-exponential and it has a lower activation energy. So it's going to be faster, okay? Let's actually just punch this one out in Excel together. So in Excel, let's go ahead and do this. Let's say we want temperature, we want our diffusion coefficient, we want time, and we want a cost per hour function, right? Let me make this big. So temperature, we decided that we're never going to go above 1082 or whatever, right? So let's just start 1085, we'll go 1080, 1075. We'll drag this down to some number. All right, we'll drag it down to, I don't know, 500 degrees, okay? So that's easy. Let's see, our next step is we're going to do, the total cost is going to be the cost per hour times time, right? So diffusion coefficient, since we're doing nickel and copper, it's going to be D naught multiplied by the exponential of the negative activation energy, right? So D naught was, in this case, it's 2.3 centimeters squared per second. So 2.3, that's centimeters squared per second. So to turn that into per hour, let's multiply that by 3,600. That's centimeters squared per hour, right? Since we have a cost per hour, this is going to make it cancel out, right? Multiplied by the exponential of negative 242,416 divided by 8.3144 multiplied by, we need to multiply this by the temperature that it's at. And that's right here, but that's in Celsius. We need to convert that to Kelvin, so 273. So that's our diffusion coefficient, and that has the units of centimeters squared per hour, right? So we send that all the way down. Next up, so we've got diffusion coefficient at all these different temperatures. So to figure out the time, we know what x is. X isn't changing. It's equal to 0.005 centimeters, right? So we can rearrange and solve for time. Time is going to equal this number squared divided by the diffusion coefficient, right? So time is going to be equal to 0.005, that's in centimeters. Sorry, that needs to be squared. Divide that by the diffusion coefficient, right? That's how much, that's the time in hours that we need, okay? So send that all the way down. And just like we expected, at high temperatures, you don't need as long. At low temperatures, you're going to need way long times, right? So now our cost per hour function, we don't know what the cost per hour was at 1200, so just call it like $1. Who knows what it is? We're going to do relative, right? So it's 1 times 1 minus 0.5. This is raised to the 1200 minus our temperature. All right? That we don't need to put that into Kelvin. We're still taking a difference in temperature. And then we divide that by 100, and we're in business. Yeah, so by the time that we've gone from 1200 down to 1085, that's basically should be cut in half, because 1200 to 1100 would be in half. We're down to 0.45. So this looks like it's working. Take that all the way down. It's getting cheaper and cheaper and cheaper. Down we go. So we've got our time and our cost per hour, so we can come up with total cost. This is just going to be equal to this multiplied by that. We're business, right? So here we go. Send it all the way down. And what's it doing? So now let's plot that versus insert a graph. And there we go. So that's our cost. So what's the takeaway? Again, y-axis is cost, x-axis is temperature. What do you do? Brandon, what do you do?
The closer you can get to that melting point, that actually reaching it, here's a cheaper example.
In this case, with these numbers, yeah, you'd say high temperature is costly, but the benefit, this exponential increase in mobility, makes it worth it because things are going to diffuse so much faster.
Yeah.
You should take it all the way up as close to 1082 as you think you can without melting it locally, because it's just going to get cheaper and cheaper to do this process. Any questions on this? Yeah.
If you were doing this for real, is there like a safety factor where you wouldn't want to go this close to
Yeah, in fact, that's a great question. Next chapter, after the midterm, when we come back, I think we jump right into chapter 11. I'm pretty sure we do. And that is on kinetics. And kinetics, basically up till now, we've assumed that everything reaches thermodynamic equilibrium. And in the real world, there are kinetic barriers, right? So for example, the demo that we're going to do on the first day you get back after the midterm, we take water and we supercool it below the temperature where you'd expect it to freeze, and it doesn't freeze. It's still a liquid. And then we do some cool stuff with it, right? So just like this, when you're heating something up, technically you can go slightly over the temperature where you expect it to melt and it'll still survive. In practice, I guess it would depend on what you're making, what your cost is if it fails. But yeah, you never take it right up to it. Like when I buy a furnace, when they say that it's good up to 1600 degrees Celsius, I tell my students never, ever, ever to take it up above, say, 15. Because, I mean, you're just asking for trouble, basically. That's what it's rated for, so you go a little bit less. Yeah, Arthur?
How would vacancies affect the whole cost per hour?
That's a good question. What would vacancies do to this question?
Do you need more energy for vacancies or less?
Well, vacancies are going to happen. They're thermally activated. And the diffusion coefficient, we know that it increases exponentially, right? If we go back to our here, it's a thermally activated process. Part of that is because there are more vacancies. That's why the more vacancies there are, the faster the diffusion process takes place. So it's accounted for in the D, right? In this D coefficient, the diffusion coefficient, that's accounting for vacancies. Any other questions on this before we move on? Okay, about 10 minutes left. There's a review session. Is it tonight, Christian? Or is it tomorrow night? The TAs will hold, is that in this room, we think? Probably in this room, unless the class is scheduled unusually. Come to this room tomorrow night, 5:30, for a review. And then we've got 10 minutes left today if you have other questions. So anything I can clarify on this upcoming midterm? Brennan?
What was the first chapter we started after the last?
Good question. So things that you're on the hook for are from chapter 4, polymers, which we didn't do much on in the last midterm. So that's chapter 4. Then we did chapter 5 on imperfections, things like vacancies, dislocations. Chapter 6 on diffusion. We did chapter 7 on mechanical properties, chapter 8 on deformation mechanisms, and then chapter 17. So it's 3 through 8 and 17. Sorry, 4 through 8. Sorry. 4 through 8. However, if you're going to study something, study the study guide, right? The TAs have the exam. They're going to give me some feedback. By tonight, we'll post any tweaks we need to make to the study guide. Arthur? I don't know, but again, even if there is a practice midterm, I would strongly suggest spending your time on the study guide, because the TAs, when they put up a practice midterm, it's their best guess, but the study guide is the exam, right? I write the exam and I say, well, that question is on, and I don't got it in front of me, but Fick's first law for maths. Okay, that's it. So I'd spend your time studying on that. Yeah, Thomas?
The graph is plotted diffusion over time.
Diffusion over time. Which plot? Is that the one we did in Excel? So this was plotting the total cost on the y-axis versus the temperature at which you decide to do your annealing step. And the higher you did this annealing step, the shorter your time was. And the lower your temperature, the longer this time was.
Yes. So how did you determine which temperature to use?
Oh, because looking at it, cost goes down at higher and higher temperatures. Right? If you wanted to be sure, you could plot this as like a logarithmic. You could change the axes, and you could say, is it really decreasing? And you'd say, yep, that's definitely always decreasing. So it's in our interest to anneal this as high as we can without melting it. And the phase diagram tells us where that point is. Yeah? Absolutely. Again, just like before, you can bring in notes, a note sheet. This time you can bring in 3. It's the third midterm. You can bring in 2 from before if you want, and a third one. Or make 3 new ones if you want. I don't care. This one is, we covered so much material, I didn't take anything from other exams. This one is just chapters 3 through 8 and 7, 4 through 8 and 17. Other questions I can answer? Yeah. Okay, WLF equation. Good question. I took that off of the exam because the TAs reminded me that I forgot to make a homework question on that, and I don't want to test you on something I haven't given you a homework question on, so I took that off. So you can kiss it goodbye. The WLF viscosity equation. I'll make a note of that when I make an announcement tonight. So if you don't know what it is, don't worry. It's not on the midterm. Other questions I can answer? Yeah. On which formula?
Y minus Y1 over X minus X1.
Oh, okay, linear interpolation? Yeah. Probably not. I don't think it does. I have to think about it. I never used this formula until a few years ago when a student pointed it out to me. I always just manually did a linear interpolation. Like, you got 2 points of a line. You got 2 points, make a line to go between them. You know the slope, the intercept. I just did it that way. This is just an automatic way to do that. Yeah? Go ahead.
How do you tell if the diffusion is going to be a steady state or not steady state?
Great question. If a question says anything where the conditions, the boundary conditions, are changing with respect to time, it's non-steady state. It's Fick's second law. What do I mean by that? If you're something is, if you've got this ball of molten nickel that you see on the internet all the time, they'll take like molten hot nickel ball and they'll put it in like water. You know that the temperature change, which is driving thermal transport, is changing. Because you drop that thing in water and the nickel ball is no longer at its same temperature. It's changing temperature, right? However, if you do something where like a home, it's cold outside, but it's warm inside, and those boundary conditions aren't changing with respect to time, that's Fick's first law, right? So if your boundary conditions, like the temperature or the concentration, is changing with respect to time, it's Fick's second law, and you have to do the more complicated math with the error function and all that. And again, the error function solution that we showed you, this is just one solution. This is called the semi-infinite solution, this or whatever. There's lots and lots of other ones, right? If you're doing diffusion like out of a hollow sphere or all these other things, you have to write, there's different expressions. When you take PDEs, which you all will at some point, you'll learn the basics of how to go about doing that. Other questions I can answer? Yeah.
For example, what's the boundary condition that's changing with respect to time?
So the surface temperature of diamond is changing. It started out at 0. The whole diamond was 0. You put it on a hot plate, and now the surface temperature it went from 0 to 200, right? So there was this change in condition. Yeah. Okay. Other questions I can answer? Got another 5 minutes still. Yeah.
Tauntaun problems are Fick's first law.
Yeah, like for example, the tauntaun problem from last class. That was Fick's. Well, I don't know where it was. Oh, it's in the homework. Yeah, that's a Fick's first law. You're assuming, and I think I even stated it. I say technically, Luke, he's getting a little bit colder, and so dt dx, the driving force, that temperature gradient difference, it's technically getting smaller. So you should have to use Fick's second law, but we're going to make an assumption that it's still pretty small, the change. So you can use Fick's first law.
You'll mention that, right?
Say again?
If we have to make an assumption, you'll mention that.
Yeah, I'll make that clear. Takar?
Do you need to know the names of the columns?
Do you need to know the names? Yeah, the basic ones, you should know the names. The really easy ones, you should be able to draw the structure. Polypropylene, that looks like polyethylene, which is just carbon-carbon, hydrogens above and below. But polypropylene, you took one of those hydrogens and you put a CH3, a methyl group there, right? So the really easy ones, I'm talking like polypropylene, polyethylene, Teflon, those ones you should be able to draw. I won't make you draw on the hard one like polycarbonate or polymethylmethacrylate. Other questions? Yeah. Yeah. My what table?
Error function.
Yeah, if there's a fixed second law question on the test, I'll provide the error function. So don't use note sheet space for that. Yeah.
Could you maybe post examples of when we would use Fick first versus Fick second so we can have more clarification about?
Yeah, maybe on the practice exam, if the TAs do post that, you'll see examples of cases where you use one or the other. That's maybe where we'll do that. The homework solutions, I've got them all done except for I need to fix one small thing on homework 7. So now that homework 8 is turned in, I'll make sure that all the homework solutions are up. You can double check that you followed how to do everything correctly. Anything else? 4 more minutes? Yeah.
On campus, you're missing a few of the completed lectures with your notes written in them.
Oh, like the after the class with scribbles, you mean?
Yeah.
Oh, I'll post those. Yeah, I can do that after class today.
What time are you going to post the review from tonight?
The study. So the study guide updates tonight. As soon as the TAs get me back the exam, can you get me back at some point tonight? Okay. So by 7 or 8 tonight it'll be up. Anything else I can answer? Okay, we'll see you on, today's Wednesday, we'll see you on Friday for the exam.